Welcome to lecture 23 of the course Marine Propulsion. Today we will discuss ship powering performance prediction. The key concepts covered in today's lecture will be propulsion factors from the model tests, scaling of the wake fraction, ship powering extrapolation from the results of model self-propulsion tests using the data from resistance and open water tests, and finally we will use some correction factors to relate the full scale powering to the values that we get from full scale trials. Just a brief background that we have discussed in the last class. The self-propulsion test includes the performance of a propeller and a ship hull together, where the propeller is acting behind the ship hull, and in different forward speeds we estimate the propulsion performance of the ship in the model scale, and from that we have to estimate the hull propeller interaction parameters, that is the wake fraction, thrust reduction fraction and relative rotative efficiency in the model scale, and from these propulsion factors we will estimate the full scale powering performance based on standard ITTC recommended methods. And finally, the delivered power and revolution rate of the ship propeller at given ship speeds required to be calculated to estimate the powering performance of the ship in the full scale. Now, the scaling of the wake fraction is very much required to get the effective performance characteristics in the full scale. Why? Because the Reynolds number is very much different between the model scale and the full scale. As we have discussed multiple times that we maintain Froude number similarity in ship model testing, and hence the Reynolds number is very large in the full scale and very small comparatively in the model scale, which leads to a huge difference in the frictional forces and the boundary layer flow pattern between the model and full scale. Because of that, the wake in the model scale is different from the wake pattern in the full scale, because the propeller works in a region which is disturbed by the presence of the ship. The wake fraction that is computed at the propeller plane in the model scale has to be corrected to get the wake fraction in the full scale, because the velocity patterns close to the boundary layer in the stern region of the ship will be different in the model and full scale. Here we will look into the wake scaling method recommended by ITTC for single screw vessels. The full scale wake fraction WTS is represented as a function of the model scale wake fraction, which is calculated using thrust identity. Here in both cases W with a suffix T is used, S again for the full scale ship and M for the model scale, and T represents that we are using thrust identity here for the calculation as a recommended case. So, the full scale wake fraction is related to the model scale wake fraction with the value of thrust reduction small t, and a constant 0.04 here is used, which value is basically due to the contribution of the rudder in the self propulsion test. As the rudder is in the slipstream of the propeller, it also impacts the wake fraction. Because of that, a value of 0.04 based on certain correlation, this value is estimated, and this is used as a constant in this particular relation, and again it is related to the frictional resistance coefficient CF in both the model and full scales along with the roughness allowance, because that is the major impact due to the change of Reynolds number between the model and full scale. So, once we estimate the wake fraction in the model scale, this simple equation can be used to calculate the full scale effective wake fraction for single screw vessels. Now, for twin screw ships, it has been observed that the scale effect on the wake fraction is very small. One of the reasons being that the two propellers are not in the central line of the ship, so the blockage effect is less on the propeller plane, and hence for twin screw ships normally there is no correction used for scaling of the wake fraction, and the model scale wake fraction itself is used to estimate the full scale performance. Now, after estimation of the propulsion factors in the model scale, we will do the ship powering extrapolation in the full scale. So, we have the wake fraction, thrust deduction and the relative rotative efficiency, and we can apply the standard ITTC method to get the full scale wake fraction from the effective wake fraction using the equation that was shown in the last slide. For the thrust deduction and relative rotative efficiency, it is assumed that they are free from scale effects. The first step here is to calculate the thrust of the ship, the total thrust in the full scale. So, we have the resistance of the ship that we get from the resistance test. What do we do in the resistance test? We measure the total resistance in the model scale and use standard ITTC extrapolation procedures to get the full scale resistance of the ship RTS in the full scale. So, that RTS divided by 1 minus thrust deduction will give us the thrust of the full scale ship. Now, one thing is very important here, because this is for the full scale ship, there is no FD term here. In the relation between resistance and thrust for the model scale, because it was done at the ship self propulsion point, the tow force term FD was there, which was the screen friction correction force. In the full scale, we will have the resistance and thrust directly linked with the thrust deduction factor as seen earlier. So, once we have the full scale resistance of the ship, we can divide by 1 minus T to get the total thrust in the full scale. Now, the next step is to estimate this factor Kt by J square in the full scale, which is a very important step for the powering performance estimation. Why? Because we do not yet know the RPM of the propeller in the full scale. So, in order to enter into the open water diagram, we have to use a factor or an expression which is devoid of RPM. Now, Kt is thrust by rho n square diameter to the power 4, and J is Va by Nd, where Va is velocity of the ship into 1 minus wake fraction. We can write wake fraction with a suffix s for the full scale by Nd, right. So, Kt by J square will be T by rho n square d4 into n square d square into Vs square 1 minus wake fraction square, right. And we see that the n square terms cancel each other, and we can get from this T by rho 1 minus wake fraction square Vs square diameter. Now, because we are doing it in the full scale, I can write ds for the diameter square, ts for the thrust. So, this is matching with the expression shown here. One additional term here is the number of propeller. If this is a single screw vessel, so this will be 1, but for twin screw vessel, this number of propeller term will be 2. Now, why we are using number of propellers here? Because the open water diagram is for one single propeller, and from RTS by 1 minus T we get the total thrust of the ship. Now, we have to convert that total thrust into thrust per propeller to enter the open water diagram for a propeller. Okay, that is why it is divided by this term multiplied by number of propellers. Okay. So, finally, we get a term which is independent of RPM, and we will see that RPM will be an output from this calculation. So, we are using this kT by J square term here. Now, in this term, the total thrust in the full scale is known, number of propellers is known, and wake fraction, speed of the ship, diameter, everything is known. So, we should be able to calculate kT by J square for different speeds. Now, for each model speed corresponding to that, we have a full scale ship speed, and we can calculate kT by J square based on our model test results and the results from the resistance test. In the next step, we will use this value of kT by J square to enter the open water diagram in the full scale. Now, we have also discussed how to get the full scale open water diagram from the model scale if we are correcting for the Reynolds scale effects. That we can do using ITTC standard procedures, or some towing tanks have their own way to get the full scale open water diagram from the model scale. Now, we enter using kT by J square, and for that kT by J square from the open water diagram, we can get the corresponding value of J for a specific speed of the ship, that we name it as JTS, because we are using thrust identity, in that sense kT by J square identity. So, we name it JTS, which is the advance coefficient in the full scale, that is why S is used for the full scale ship for a particular speed. Now, for that advance coefficient, we can calculate the RPM. So, for any speed, once we enter the open water diagram with kT by J square, we can calculate the corresponding J, and from J we can calculate the RPM. Why? Because J is VA by ND, and VA is nothing but Vs into 1 minus wake fraction. So, N will be Vs 1 minus wake fraction by J into D, J into D, J here is JTS. Now, we have multiplied it by 60, because in the full scale ship the propeller speed of revolutions is typically mentioned in RPM. So, we have converted the RPS value to RPM by multiplying with 60. So, once we have the RPM in the full scale, the same J can be used to calculate the corresponding KQ from the open water diagram for the ship in the full scale, and this KQ can be used along with eta r, which we had already calculated in the beginning. So, this KQ from the open water diagram divided by eta r will be the behind condition KQ in the full scale, and eta r is considered to be devoid of scale effects for standard calculation purpose. So, we can use these values to calculate the delivered power of the ship in the full scale. So, the delivered power PD is given by 2 pi NQ, where Q is KQ. Now, KQ is KQ in the behind condition. So, it will be KQS by eta r, because we have calculated this KQS using this JTS from the full scale open water diagram, multiplied by rho n square diameter to the power 5. Okay. So, if we multiply this Q with 2 pi n, we will get this particular equation for PD. So, now instead of Ns, we have Ns by 60, as Ns is mentioned in RPM, and for PD, because full scale power is typically expressed in kilowatt. It is divided by 1000 to get the power in kilowatt. Okay. So, in this particular expression, all the values of these parameters are now known. So, we are in a position to calculate the delivered power in the full scale. Now, the brake power of each engine can be calculated from this delivered power divided by eta s, which is the shafting efficiency, the mechanical efficiency involved in the shafting components, which is typically having a value of around 0.97. So, we have the engine brake power in the full scale ship. This is how we get the propulsion factors from the model tests using the results of the self-propulsion test, the open water test, in addition to the resistance test, and we use standard extrapolation procedures for ship powering prediction from the model test results using kT by J square similarity to enter into the open water diagram in the full scale and calculate the RPM and delivered power for the full scale ship. Now, this powering calculation that we have just done is based on the model test results, but a correlation factor also is often applied to match these powering prediction from the model test with the measurements that are obtained from full scale trials. Trials means the estimation that is done during the trialing of a new build ship. So, when a ship is built, it has to undergo sea trials for estimation of different parameters for a ship. One of it is the powering performance. Now, from the full scale trials, the value of the powering performance parameters of a ship can be correlated with the powering predictions that are done from a model test facility, and based on these comparison of results for previous model tests, a correlation allowance is developed for different types of ships. Now, different model test basins have different types of facilities. For example, the length of the tank, the capacity of the tank in terms of the model size, the model speeds will be different from one towing tank to another. Now, based on this, there will be some bias errors in the estimation of ship powering performance from different towing tank facilities. So, what is done typically is based on the full scale estimations from trials, the powering calculation obtained after extrapolation from the model tests that we have seen in the last slide are compared, and a statistical analysis is done based on specific ship types over many years of experience for a particular facility, and they are computed into a correlation factor which is used in the powering performance extrapolation for future ships. So, each model test that is being done is used in this statistical process, and these correlation factors are defined over time, so that a particular model test results when extrapolated to full scale can be effectively converted into a result that can be used for a full scale ship in an actual trial condition. So, these systematic errors that can arise in different test facilities are basically included in this correlation factors. So, as per ITTC recommended guidelines, there are different kinds of correlation factors which are used for model testing in naval architecture. For propulsion tests, the commonly used correlation factors are CPCN correction factors, which are the correction factors for propeller revolution rate and delivered power. Now, CP is the trial correction for the delivered power, and CN is the trial correction for the propeller rate of revolution at speed identity. So, if we have the NS, we have seen that in the powering performance extrapolation we have calculated the revolution rate of the propeller in the full scale, which was ns, which is the value that is obtained from the model test after extrapolation. Now, this ns, using this correction factor Cn for the propeller rate of revolution, we can convert it to Nt, which is the trial value of the propeller revolution. Similarly, we can use another correction factor Cp to convert the calculated value of the delivered power of the ship in the full scale to the trial value PdT. So, in this way we can convert the values which are obtained in the full scale from the model test extrapolated results to the trial values using some correction factors which are based on analysis of previous model test results as well as full scale trials for similar kinds of ships. So, these correlation factors value will be different for different model test facilities, and they are based on previous experimented values and experience. Now, this will be all for the part on propulsion tests and powering extrapolation to the full scale. Now, some other measurements that are done related to propellers are wake measurements, which are typically done to assess the wake velocities behind the ship hull in the propeller plane without the presence of the propeller. So, it can be done using a circulating water channel, as we have seen earlier, and these channels have a test section where we can keep the body of interest, in this case the model, and behind that some flow measurement device like pitot tubes can be used to estimate the velocities which are measured in three different directions, basically in the axial, radial and tangential directions on the propeller plane, to estimate the nominal wake field behind the ship. And this is used to have specific insights into propeller designs which are tailored for a specific ship type based on the wake velocities, and also the stern design of the ship. The effectiveness of the design in certain aspects can be checked in terms of the wake velocity which are measured in these wake measurement devices in the circulating water channel. Wake measurements can be done in both towing tank as well as circulating water channel, and they can be used effectively for certain design purposes. Another set of experiments which are popularly used for ship propellers are cavitation experiments. Cavitation will be covered in details in the next classes. I am just giving a brief overview of cavitation experiment because this falls under the different types of model testing we do for marine propulsion. So, in a cavitation experiment, what we do is the propeller performance is measured in cavitation tunnel. So, the propeller thrust, torque and efficiency are measured for different flow conditions in a cavitation tunnel, where in addition to the propeller RPM and the velocity of advance, we can also change the pressure. So, in a cavitation tunnel, the pressure can be controlled, and that leads to cavitation phenomena, or that means occurring of cavitation over different propeller blade sections, depending again on the propeller design and the operational conditions, and it can be observed for different pressure conditions which relates to the cavitation number. So, the idea of these cavitation experiments is to assess the performance of a propeller under different conditions of cavitation number and obtain the open water diagram for different pressure characteristics which is related to the cavitation number on the propeller. We will continue with propeller cavitation in the next class. Thank you.